yesterday is energy and radiation. And I think I read from like, I went over everyone's introductions, and I think this was like the least favorite one for everybody that they were not looking forward to is radiation, or for most people, but it's really not that bad. It's a lot of stuff that's going to come up later in the rest of the class. Okay, so this lecture just goes over why energy matters, the types of energy. That'll be important. A really important thing you'll need to remember is the way that heat and energy can be transferred. And then we'll go over electromagnetic radiation, the electromagnetic spectrum, and then radiation and how it transfers in our atmosphere. And if I'm going too fast, just tell me I am. So Myra wanted to play this yesterday, but I guess campus was having a really hard time with Wi-Fi, and she couldn't play it. But I don't know if anyone remembers this. It was in 2011. This was the EF4, EF5 that hit Tuscaloosa, the tornado that hit Tuscaloosa, Alabama. It killed, I think it's like number 2 for killing the most people with one tornado. And what she wanted you all to like think about was when you're watching this, thinking about energy and how much energy could be like in this like tornado, what kind of energy it could be, where it's coming from. And she kind of just asked questions about that. I think someone just like described a tornado to us, and that was about the answer. But so when you're looking at weather and climate, basically, she just wanted you to think about like the kind of energy, the types of energy that could be occurring with like these types of weather. All right, so there is a difference between energy and heat. So energy is the capacity to do work or move matter. So energy is going to occur when a molecule, so something as small as a molecule could be moving around, that'll be energy. Whereas heat is going to be the flow of energy between molecules or between bodies. So there are 2 different types of energy, which we talk about. They should look really familiar from like high school. We don't really talk about them much later, but they're still important to remember, and they might come up on the exam. So kinetic energy is the energy of motion, while potential energy is stored energy. And there's usually an example. I wish that I had like a whiteboard to like draw on too, but there's usually an example of like you have a hill and someone's pushing a ball up a hill. And as they're pushing the ball up the hill, they're exerting like potential energy. And then as the ball like goes over the peak of the hill and then starts to roll down the other side of the hill, it's releasing or giving out kinetic energy. So potential is the stored or the energy, let's see. Kind of like the buildup of energy, whereas kinetic energy is like the release. And there was another example I saw of like someone blowing up a balloon, and that's potential energy, and then letting the balloon go and letting it just like go all over the place while it's releasing the air that you just put into it, and that's kinetic energy. So hopefully that makes sense. Then there are 2 different types of heat. This is going to come up a lot during the rest of the course. There are 2 types of heat: sensible heat, which can be sensed by humans. So you can sense it by watching the temperature change. I'm not being too loud, am I? Okay, good. And then there's latent heat, which is hidden heat. Latent heat occurs during a phase change, and it cannot be detected by a temperature change. Latent heat is how a lot of activity in weather and climate systems, that's where they get their energy, is from latent heat. Latent heat, for example, is what like feeds hurricanes. So that'll be something that comes up. Myra pronounces it latent heat. So if you hear her say latent, and it's either or, but if you hear her say latent heat, that's what she's talking about. I pronounce it latent. All right, so this is just kind of going over what I just talked about, except on the molecular level. So kinetic energy is going to be the movement of energy. In atoms where there's more motion, there's going to be a warmer temperature. Where potential is the energy that's contained or stored within the molecular bonds. An example of like kinetic movement or energy, like compared to or relative to temperature. In a solid, for instance, if we're talking about water, like solid ice, you're going to have a lot of vibrations because the atoms are bonded together, but they're not able to move. So there's not as much temperature or energy that you can measure by temperature. So they mostly just vibrate. In liquid, there's a little bit more movement, not as much movement. And then once you get to like a temperature to where that liquid would evaporate into water vapor or a gas, there's going to be a lot more movement. So the molecules are a lot more mobile. So there's going to be a lot more energy. They're going to be warmer. So there's warmer temperature in air because, you know, water can only be heated up to like 100 degrees Celsius before it evaporates into water vapor. So it's just an example of what molecules are doing in like different states. Is everyone good so far? Okay. So I feel like I'll keep getting ahead of myself, but what occurs during warming and cooling. So this is just kind of talking about what happens to energy as something is becoming warmer and then as something's becoming cooler. So as something's becoming warmer, it can't just become warm out of nowhere. It's taking heat or energy out of its surroundings, and that's how it's able to heat up. Whereas if something is cooling, it's losing energy and releasing energy out into its surroundings. That's, for example, what happens with hurricanes. So I study hurricanes, so I'm going to use that as like an example a lot. But hurricanes get all of their energy from ocean water. As ocean water is evaporating, it's cooling the water, the ocean water below it. So it's releasing that energy up into the air, and that's what hurricanes use as like their fuel for power. Is that energy that's being released by the water as water's evaporating, and it's cooling the water below it, and that energy that's being released is like allowing it to gain power. Kind of a okay example because I'm also talking about evaporating, that's something getting warmer, but basically when something warms, it's gaining energy from its surroundings. So something cools, it's losing energy to its surroundings. In simple terms, heat or energy is transferred from higher temperature to lower temperature objects. So if you have, you have a warm object, it's going to transfer heat or energy to its cooler surroundings. And if you have a cold object, it's going to take heat or energy from warmer surroundings. All right, so this I can almost guarantee will show up on an exam. These 4 types of ways that heat can be transferred. The first one, probably the most simple one, is conduction, which is just energy transfer through direct contact between 2 objects. So usually in this example, we talk about like a pot of boiling water. So that heat, I don't know if you can see my cursor, I think you can. But that heat that's coming from the stove is heating the water above it. So something that's warmer is transferring energy to something that's cooler. I'm going to go to radiation next. Radiation is just transferred through electromagnetic waves. Like for instance, if it's a hot day and you're looking at like a asphalt or something outside and you can see like those waves coming up, that's radiation. Advection is the transfer of energy moving horizontally or sideways. In this example, they're just moving it literally like from the pot from like one side to the other. We won't talk about advection very much. I saved convection for last because that one is going to come up a lot during the rest of the semester. Convection is like advection, but instead of the transfer of heat horizontally, it's a transfer of heat vertically. And when you have like a vertical transfer of heat, it can sometimes create what's called a convection cell, which are what these little swirls are right here. And that'll come up in a lab that's coming up too. Convection is also how weather occurs a lot of the time. Rising heat from the surface, creating clouds, and then the cold air cooling at the top of the atmosphere, then dropping, and that creates a convection cell. And if you don't understand that right now, you don't have to memorize it. We're going to be talking about convection a lot the rest of the semester. So this is just like an introduction to it. But these 4 types of ways that heat is transferred will definitely come up on an exam. I haven't seen your exams, so I'm just saying that because I've been in this class way too many times and it usually shows up on an exam. And these are just more examples of like the types of transfer. Conduction because you're touching something, these puppies' feet is probably getting burned from the asphalt, and that's conduction. Advection could be like wind moving sideways and pushing heat from like the ocean onto like the surface or onto land. And then convection would be, an example would be a cloud forming. So is everyone good with those four so far? All right, hope I'm going fast enough. All right, so now we get to one of the fun parts, which is the electromagnetic spectrum. So I'm literally getting this from Wikipedia. Electromagnetic radiation are just waves of the electromagnetic field propagating through space, which can include visible light, radio waves, gamma rays, X-rays, ultraviolet light, etc. And all of those form part of the electromagnetic spectrum, which is this right here. Each type of energy that is within the electromagnetic spectrum is going to have a different wavelength. So a different size wave. Some of them will be short, some of them will be long, depending on how much energy it contains, which we'll talk about in just a second. Some of it's visible and some of it isn't. But all of them have different wavelengths and frequencies. So these are electromagnetic waves. Incoming solar radiation, comprising energy traveling with different wavelengths, etc. Some of them are going to be, again, short. So this is called shortwave radiation if they have short wavelengths, and the wavelength is just going from one amplitude to the other and measuring that. So this is a short wavelength, whereas up here, we would be going from this amplitude to this one, and that's a much longer wavelength. So that would be long wave radiation. This is kind of looking, since it has the colors, it's kind of giving the example from like a visible light. So visible light is going to be, and we'll go over this again in a second. Visible light is going to be like the rainbow. You're going to have shorter wavelengths down near violet. And then when you get up to red, you're going to have longer wavelengths. So there are two radiation laws or thermodynamic laws that come into play that we will talk about in this section and then probably never talk about again, but it will probably show up on your exam. You just need to know, and I think it's on a quiz too, like your literally quiz two, where it asks, or it might have been quiz one, no, it would be quiz two, where it asks you like the difference between the two laws. The first law is the Stefan-Boltzmann law, and it's just talking about how hot an object is, or how much energy is being emitted from an object based on how hot the object is. So for example, if you have an object like the sun, which is like 6,000 Kelvin, and Kelvin is just another way of like, just another way that we measure temperature, just used a lot in science. So if it's at, the sun's at 6,000 Kelvin, it's going to emit a whole lot of energy because it's a really, we call them like a body, a radiative body. So a really hot radiative body is going to radiate a lot more energy, whereas the Earth is only around like 283 Kelvin. And so it's not going to emit nearly as much energy as the sun would. And that's all that law means, is that the hotter the object, the more energy it releases. So in simple terms, warm objects are going to emit more radiation than cold ones. And there's not really, there is like an equation that goes with it, which I would write out if I had like a whiteboard. You don't need to memorize the equation. It's just kind of like fun to see for me, I guess. There is like an equation that can calculate how much energy is emitted depending on the temperature. But when we talk about it in this class, it's more just like comparing. So which one is going to emit more energy, the sun or Earth? The sun will. So more like just comparing like relative bodies than like using the equation. You're not going to be doing that at all. So everyone good on that law? I know this is like a really boring part of the class, but I'm going to skip this part. All right, so the next law, sorry, I just skipped the last part because we pretty much just already talked about it. So the next law is Wayne's law. And that's the relationship between temperature and wavelength. So cooler objects like the Earth are going to emit longer wavelengths, whereas warmer bodies like the sun is going to emit shorter wavelengths. And shorter wavelengths automatically mean that they're faster and that they have a lot more energy. So the sun is going to be a lot warmer, therefore it'll have shorter wavelengths, faster wavelengths, and a lot more energy coming from it. The Earth will have slower, longer wavelengths and a lot less energy being emitted from it. And that's all this law means. So it gives the same example. It's just basically comparing the Earth and the sun. And that's what you really need to remember from both of these laws. So warm objects emit shorter wavelengths, cooler objects will emit longer wavelengths. So there are several parts of the electromagnetic spectrum. This is kind of, if you forget where they're at, this is kind of where the shortest and the fastest will be. It's going to be at this end. You can also think of it as the violet end. That's how I like to think of it. It helps me remember, especially with the visible light section, like what side has the shorter wavelengths. And then the more like infrared side or red side is going to have longer wavelengths. Longer wavelengths or infrared radiation is going to be emitted from the Earth more so, while visible light and ultraviolet radiation on this side is what the sun emits. The sun can emit all of this. I mean, it's obviously like ridiculously hot, so it's going to be emitting all sorts of very short, high energy, fast wavelengths and radiation. By the time that radiation reaches Earth, the gamma and X-rays are kind of gone. There's very little of it left that actually makes it, scatters, or just kind of like gets absorbed by other particles in space before it hits the Earth's atmosphere. So a lot of what enters the Earth's atmosphere from the sun is ultraviolet and visible light. A little bit of infrared, but it's more like near infrared. And we didn't really go over that very much. So these are the two big ones that enter the Earth's atmosphere that come from the sun. And then it's absorbed by the Earth, and then the Earth re-radiates it out as infrared or longer wavelengths. And remember that red is going to be longer, have longer wavelengths, whereas violet is going to have shorter wavelengths. And the shorter, the more energetic it is. Ethan, do you have your hand raised, or is that just from before? I just want to make sure.
No, I'm good. Thank you.
Okay. All right, so shortwave versus long wave. This is kind of like going over what we just said again. Energy reaching the Earth is mostly at wavelengths of visible light and UV or ultraviolet light. So the sun emits shortwave radiation in the way of visible light, UV light, gamma rays, etc. These are the two that reach the Earth's atmosphere. The Earth then absorbs that shortwave radiation and then re-emits it as infrared radiation or long wave radiation. And it's not the energy, this is kind of important to point out, it's not the shortwave energy that heats the Earth. It's the absorption of that energy and then the Earth re-radiating it. That re-radiation is what keeps the Earth's surface warm. And that's where like the greenhouse gas effect or greenhouse effect comes into play, which will come up later. But that's what keeps the Earth warm, not actually like sunlight, but the Earth absorbing that sunlight and then re-radiating it or emitting it again. So it comes in a short wave and then leaves as long wave. And these are online in case I'm going too fast, and you're also allowed to tell me if I'm going too fast. All right, so this is just doing the same thing again, exactly what I just said. Short wave coming in, long wave coming out. So short wave would be ultraviolet, visible, short wave infrared, and then thermal or long wave infrared is what is re-emitted back into space. So a breakdown again of what comes from the sun. About 47% of it's going to be visible light, so this spectrum. About 8% of it is ultraviolet, X-ray, gamma, wavelength. There's not a lot of these because they're very high energy, and by the time that they've reached the Earth's atmosphere, they're mostly gone. Even if they do make it to the Earth's atmosphere, they barely make it to the inner portions before they get knocked out or absorbed by protective particles or molecules in the atmosphere, which in this diagram, they call it the ozonosphere. That's different. I've never seen that before, but it's true. In the stratosphere, basically the only, which is that second, I think was everyone here last Friday and saw the lecture on the different layers of the atmosphere? Yeah. So that second layer is the stratosphere, and basically its only purpose is that it contains ozone, and ozone absorbs ultraviolet light, which is why ultraviolet stops right here. About 95% of ultraviolet light is absorbed by the stratosphere. Only about 5% really gets through, and there's different types, which will come up in another, I think the next lecture, different types of ultraviolet light, and yeah, we'll get to that. But basically gets stopped by ozone. So what really makes it through is just visible light. Another 45% is infrared light or infrared wavelength, but it's like near infrared. And near infrared just means that it's still infrared, but it's shorter wavelengths than what is re-emitted by the Earth, or it's called shortwave infrared, which feels kind of counterintuitive, but there's shortwave and long wave. All right, so this was the activity we did in class yesterday, was just patterns. And I'm not going to make you guys do them, like you guys are all excused from in-class activities while you're out. But this is just something to think about, is what patterns do you notice in shortwave and long wave radiation. So this map over here is the January average of shortwave radiation that comes in from the sun. And then this is the pattern of long wave radiation that is being emitted by the Earth after it's absorbed the shortwave radiation. So I don't know if that's something that you guys want to do, or if you just want me to answer the questions. Basically, if you notice anything about these patterns, so there's not really, should point out there isn't a legend for this, but the red and pink is like the most incoming shortwave radiation, whereas like the blue is going to be the least amount. So most of the incoming shortwave radiation from the sun is absorbed in the tropics or subtropics. So it'll go from about 23.5 to 23.5 degrees latitude. This is in January, so the sun actually is right above, it's about right here, directly over the Tropic of Capricorn. And that's something that you'll be doing in the lab this week too. So that's something to remember with shortwave radiation, is that most of it is being absorbed by the tropics and the subtropics. Hardly any is being absorbed at the poles, because the sun is directly over this area during January. During May, this is long wave radiation that's being emitted. Yeah, and that's a lot more spread out. There's a little bit more being emitted here in the northern hemisphere, because that's where the sun is directly overhead in May. That's where you see why also you see a little bit of red up in the northern poles, whereas down at the South Pole, you don't really see anything being emitted because it's actually complete night at that point there, which we'll talk about, I think. We'll talk about one of them in this session. I can't remember which one of the next sessions that it's in. But long wave radiation being emitted from the Earth is going to be a lot more widespread, but it's still, both of them depend on where the sun is directly overhead. So I think I did that in like 20 minutes. So this is just, these are questions that you'll need to remember to practice for exams. And I don't know how we're going to be, that brings up, I don't know how we're doing exams with you guys. I think we might just wait until you get back. It's up to Myra. I don't want to speak for Myra, so I'm not going to say how we're doing exams, but it'll be as fair as possible. We'll make sure that it's done properly with you guys. And you guys have enough time to like catch up before you take your exams. Because I think that's coming up the end of next week. All right, so are there any questions about this before I move on to the next one? Everyone's good? Okay. All right, do you want to take like a 2-minute break, or you just want to like jump into the next one? That sounds like you just want to jump into the next one. Or do you want to break? Raise your hand if you want to break, like your literal hand. Okay, we'll just move on. All right, so we are talking about seasonality in this next lecture. So this is the lecture that Maya will probably be going over tomorrow, or she will be going over tomorrow. And this is about the Earth's orbit and the seasons. And these are the things that you'll be learning about. The biggest one will be probably like day length, because that connects to all of these features that we'll be discussing in this lecture. All right, so shortwave, keep calling like radiation from the sun, like sunlight, shortwave radiation. The term we'll mostly call it will be insolation. So shortwave energy from the sun is called insolation. It's called a lot of things, but that's what we'll call it over the rest of the semester. There is a solar constant, which just means that the average amount of insolation over the Earth at any given point is like 340 watts per meter squared. That can get as high as like 1,000, even in like the mid latitudes. It just depends on where you're at. So how and why does this constant vary over time and space? I don't want to rush through this. Oh, and this part, I don't know if you really need to know this, but just in case you put it on like an exam, only 1 out of 2 billion. So 1/2 billionths of the total emitted solar energy actually makes it to Earth and hits it, which is why we lose a lot of that shortwave energy before it hits the atmosphere. So a question that Myra poses is why is the solar constant different across time and space over Earth, and could it be because of the Earth's orbit? So talking about the Earth's orbit or revolution for a second, the Earth's orbit or revolution is nearly circular. There's only a difference of like at one point in early January 3rd specifically, the Earth is 147 million kilometers away from the sun. Whereas on July 4th, it's 152 million kilometers away from the sun, which is the difference of like 5 million kilometers, which it's not that much. It does cause a little bit of change in the climate. And for us in the Northern Hemisphere, it's a little hard to memorize because it's counterintuitive for us, because when we're closest to the sun, which is called the perihelion, on January 3rd, we're in the midst of like our winter. So it doesn't feel like we would be closest to the sun, but we are. And we're the farthest away from the sun on July 4th, which is the aphelion. But honestly, there are only minor variations in insolation because of this difference in distance. There's not a huge amount of difference. You still need to know these. This will come up in lab this week or next week, and could show up on the exam. But basically the answer to this question is it because of the shape of the Earth's orbit? Not really. That's not really why the sun's like insolation varies across like the Earth. So what actually then could cause the insolation variability? And variability just means like how it's different in different places of the Earth or different times of the year. So the actual answer is that it's because of the angle of the sun. So there are 2 different types of angles that you'll need to know. The most important one is the sun angle. I hate to say that, but it is more important, which is just the angle of where the sun is compared to like the horizon. And then there's the zenith angle, which is just the angle of where you're at, what is directly over you, and then how far away the sun is. This is important because we live in a place in the world that never sees the sun directly overhead. It'll never be directly like over our heads because we don't live in the subtropics or tropics, and that's where they have the sun directly overhead. So insolation is going to be spread out as that zenith angle changes. So as if it were directly overhead, we'd be getting like the maximum amount of like direct sunlight that we could. But as that angle becomes larger, we get less and less insolation, which explains why the equator is warmer, because the equator and tropics, subtropics see the sun directly overhead most of the year. So they're going to get the most direct insolation and the most energy, whereas places like where we live around 30 degrees or 30 degrees latitude, we're not going to get nearly as much, only about 87%. And then someone who lived in like Iceland would only be getting about 50%. And then someone living at the North Pole would be getting like pretty much none of it, or none of that sunlight. And there are two reasons why the sun angle matters. The first one is beam spreading. This just means how much surface the sunlight has to cover from the angle that it's at. So at a lower angle, it has to spread across more surface than it would if it was at a direct angle. These two, beam spreading and atmospheric attenuation, are pretty much, they're really, really similar. Basically, what you need to know is the more directly overhead the sun is, the more energy you're going to be getting, the less surface it has to cover, the less atmosphere it has to go through or pass through. And if you're at a greater angle, like in this example and this example, like the sun is low in the sky, there's more atmosphere it has to go through, there's more surface it has to spread across. It's going to lose a lot of energy before it actually reaches the surface of the earth. And so this is controlled by latitude and where you are latitudinally on Earth. And this kind of going back to the last slide, how this is showing like angles 0 and 30 degrees, but I kind of related these to where you are latitudinally. So latitude, 30 degrees latitude, 60 degrees latitude, 90 degrees. This is kind of how the sun is going to look as you're at different points in latitude in both hemispheres. So the equator has a high sun angle because the sun's directly overhead a lot of the time. So it'll have a lot more energy that's being absorbed by the earth. Or that's at least reaching the earth's surface. We'll get to that later. The mid latitudes, apparently it's just right. I guess that kind of depends on how you feel about like what type of weather you're most comfortable with. But it does describe why mid-latitudes have more, we have 4 seasons, whereas other places on Earth might not, like the tropics or the North Pole. They tend to have more like 2 seasons. And the poles have a low sun angle, so it's a lot more atmosphere that the sunlight has to go through to get to it, and a lot more spreading, so a lot less energy it makes it to the poles, which is why the poles are so cold, or one of the biggest reason why the poles are so cold. So sun angle is what controls this, as well as latitude, but sun angle depends on latitude. So the results, again, this is what it would look like in the tropics. This is what it looks like in Knoxville. You have a lot of like deciduous, but also conifers and stuff where you would see like in a more temperate climate than the tropics. And then you have an ice cap or ice sheet or wherever this person is. No vegetation. All right, am I going too fast? Is everyone okay? Okay. All right, so this is going to be a big thing that we talk about in the rest of the class also, is the Earth's tilt. So the reason why we have seasons is because of the Earth's tilt. The Earth is tilted, and this will be in the next slide, but the Earth is tilted at 23.5 degrees, which is why we have 23.5 degrees north and south latitude are important lines of latitude to us. As the Earth revolves around the sun, actually it does revolve that way. As it revolves around the sun, it's tilted, which is what dictates the sun angle and the day length at any given latitude, and why it changes throughout the course of the year. So these, let's see, oh, I have my highlighter on. These dates you will need to memorize. You'll need to memorize them for exams, for future lectures. They will be on multiple labs coming up. and the importance of these days. So the Earth's spin, yep, is tilted on a plane of 23.5 degrees. This will come up later, but it's 23.5 degrees now. It isn't always at that tilt. It can change very slightly. During our lifetimes, it will always be at 23.5 degrees though, so that's important. So its relation to the sun is going to vary during its orbit around the sun. So again, those dates on December 21st, the North Pole is going to be tilted away from the sun. So if you can tell, it's in complete darkness. And this is during our winter as well. So that's really easy to remember. And this is our winter solstice. And this will come up, those words, these phrases will be in the next slides too. The South Pole is tilted towards the sun. So it's going to be in complete daylight. So 24 hours of daylight. In the opposite, on June 21st, which is our summer solstice, the North Pole is tilted and completely in the sun, whereas the South Pole is tilted away and completely in darkness. And this is again during our summer and during the Southern Hemisphere's winter. So we have, and I think you guys know this, but just as a reminder, we have switched seasons between the Northern and the Southern Hemispheres. It's always the opposite. And then during March and September, which these aren't nearly as important as these two, but these are our equinoxes. And the sun is going to be directly over the equator at that point, and everyone receives even amounts of daylight throughout or on that day. All of us get 12 hours of daylight. And these are called like the transitional seasons. So we're going to be like going deeper into that. So it's just like an introduction into that. These things are horrible. We used to have to draw them in lab and luckily they took them out. They're terrible. So we're not gonna be looking at that as much. So solar declination is a latitude where the sun is directly overhead on any specific day. So like I said before in the last slide, the sun is on the equinoxes, the sun is directly over the equator. Whereas on June 21st, our summer solstice, the sun is directly over 23.5 degrees north. And then during our winter solstice, December 21st, the sun is directly over 23.5 degrees south. And that's what the declination is. It's just whatever line of latitude the sun is directly over. And it bounces back and forth every 6 months between 23.5 degrees north and 23.5 degrees south. And it's not like the Earth is actually doing this. It's not. It stays tilted. It's just the way that it's going around the sun. The sun's angle is going to change and go back and forth between 23.5 degrees north, 23.5 degrees south, and then go back up. So it crosses over the equator twice. And remember that that 23.5 degrees north is the Tropic of Cancer, and 23.5 degrees south is the Tropic of Capricorn. And we'll say that like 100 more times the next couple of lectures, so you'll remember it, and labs. All right, so the sun angle throughout the year, and this will be helpful as a hint when you do your lab next week. You'll have to fill out like a diagram that looks exactly like this. So in the tropics, the sun is always nearly directly overhead. It's either directly overhead or really close by, because it bounces in between the Tropic of Cancer and the Tropic of Capricorn, and never is directly overhead anywhere else outside of those latitudes, only between these 2 points. Each time the solar declination passes over the equator or reaches the Tropic of Cancer or Capricorn, a new season starts, which is why the first day of summer technically is June 21st, and the first day of winter is December 21st. The first day of spring is March 21st. The first day of fall is September 21st or 2nd, one of those. That's why we consider those to be the first day of our seasons, is because that's when the sun hits one of these 3 points. And again, the poles have much lower sun angles, which can get down to 0 degrees, like on December 21st, the Arctic Circle, which is anywhere north of 66.5 degrees, is going to have complete darkness. Whereas on June 21st, the Arctic Circle, or anywhere north of 66.5 degrees, is going to have complete total daylight for at least 24 hours. and then the opposite on the south poles. The circle of illumination, so this is just a really nice term for whatever part of the sun or whatever part of the earth is being hit by sunlight and whatever part of the earth is not being hit by sunlight. So when we fill these out, these diagrams on a test, which I could see this diagram being on a test, I don't know that for sure, but you would want to make sure that you make that line, that like circle of illumination, and then shade this part to show that you know this part is in darkness, whereas this part is being lit by the sun. That's all the circle of illumination is. I hate that I need to speed up, but I think I do. Yeah, so this is just more about the circle of illumination and how it's important with those 4 dates during the year, June, December, especially June and December. In this case right here, it would be the equinoxes in March and September. But again, the September solstice and the June solstice are the really important ones. There's the equinox. So you'll need to know what day you're looking at to know what side of the earth you need to shade in. You'll need to make sure that if it's a solstice, so the earth is tilted, and one of them is facing either the South Pole or Antarctic Circle or the Arctic Circle or North Pole, or which one is facing the sun, because that whole area is going to be in sunlight or in darkness. So you'll want to make sure to do that to make sure that those are delineated or differentiated between when you fill this out in like labs or on an exam. So the June solstice, again, I know I'm repeating myself a lot, but the North Pole or Arctic Circle is totally in sunlight. The Antarctic Circle or South Pole is totally in darkness. And then the opposite occurs on the December solstice or December 21st. The Arctic Circle is totally in darkness and the Antarctic Circle is totally in daylight. This is called perpetual daylight or perpetual darkness. If you're right at 66.5 degrees, which is this Arctic Circle right here, 66.5 degrees north, you will have exactly 24 hours of darkness. The farther north you get from 66.5 degrees, getting up to like 90 degrees, the more darkness or longer amounts of like darkness you're going to have during the summer or winter solstice. So starting on December 21st, you could, if you were at the North Pole, like right at 90 degrees, you wouldn't see daylight for like 6 months. Whereas if it was June or the summer solstice and you were in the Arctic Circle, you would have daylight for like 6 months if you were at like the North Pole. Iceland counts as that. Iceland hits the Arctic Circle. So during the June solstice, it would have 24 hours of daylight. I like to talk about Iceland a lot because it's my favorite country, but I mean, other than America, yay America, but also Iceland. Something else important I was going to say. There's a really creepy movie where Robin Williams is a serial killer. Has anyone ever seen that movie or heard of it? Well, it talks a lot about how like there's constant daylight and it drives like one of the detectives crazy or something because he's way up in like Alaska and it's just daylight all the time and he can't sleep. And apparently that's a huge issue for people who live within the Arctic Circle, or well, no one lives within the Antarctic Circle, but anyone living within the Arctic Circle has that issue a lot during half the year. When I visited Iceland, the sun went down at like 11 o'clock at night and then rose at 3 o'clock because I was there in August. So that can cause a lot of issues with like depression and stuff in places where those people live, if that helps you remember what happens in the Arctic Circle. So again, yeah, polar night, perpetual night, when the night lasts for a day or more. Like that, I know I'm comparing this to a lot of popular culture, but that vampire movie, 30 Days of Night, that one's a little more popular, where like the vampires come out because they have 30 days of complete darkness and somewhere in like Barrow, Alaska. Anyway, it wasn't a great movie, but that was an example of them using like the seasons as a way to like really mess with people's mental health. So if you're right at the 66.5 degree latitude line, you'll have 24 hours of darkness. And if you're right at the South or North Pole, depending on which one you're in, you could have 6 months of nighttime. This also means that at the North and South Pole, you only have one sunrise and one sunset all year, which is at the equinoxes. So there will also be in one of your, and this could show up on an exam, but it's definitely in one of your labs, your lab next week. You'll want to know which way the sun is, or the earth is moving around the sun, starting with June, and that's counterclockwise. Yeah, that's correct. And then you'll need to know like June 20, it says 22nd and 23rd. That's silly. You can say 21st or something. It depends on what book you read. It might say like March 21st, March 22nd, and it's one or the other. It doesn't, there's not really a right answer. One of those couple of days in like the third week of these months. So memorizing these like dates and then which equinoxes or which solstice it is. And then this is like if you were above like the North Pole. So you're like hovering above the North Pole. During the summer equinox, the Arctic Circle is completely in sunlight, whereas during the winter solstice, did I say equinox? I'm sorry. During the summer solstice, the Arctic Circle is completely in daylight. During the winter solstice, it's completely in darkness. I think I've like honed that in pretty well. During the equinoxes, it's split in half, and every day is going to have, or every place on Earth is going to have 12 hours of day and 12 hours of night. Oh yeah, and the direction of the Earth's rotation is always counterclockwise. So we'll be going, yeah, that way. And you'll have to like show that in this diagram, at least on your lab. So the percent of latitude line in the lit section shows how much day length or what the day length will be in that area at that, on that specific day of the year. And this is just, I guess, a really cool picture of the Arctic Circle during summer where you can see like the sun going up and down. Oh, I just ruined that. Oops. And what the sun does like during that 6 days or 6 months, sorry, of daylight. All right, so these I can do with you. These are for practice. This would be probably a participation activity in class tomorrow, again, which you will be exempt from. But there are 4 of these. So 1, 2, 3, 4. If you want to practice, you can. If you do, you want me to do them with you right now? Yeah, okay. So basically, these are the 4 days of the year that you need to memorize. You will need to remember the name of the day, the like what that day's called, solstice or equinox, the date, the solar declination, so wherever the sun is directly overhead that day, and what the day length patterns are like. So this one, the sun is directly overhead at the Tropic of Cancer, so 23.5 degrees north. The Arctic Circle is completely in daylight, and the Antarctic Circle is going through polar or perpetual nights. So this means that this is our summer. So this is going to be the summer solstice, which will be the name. The date would be June 21st. The solar declination would be 23.5 degrees north. So the sun's directly over the Tropic of Cancer. And the day length patterns, days are going to be a lot longer in the northern hemisphere and a lot shorter in the southern hemisphere. And then the equator always gets 12 hours of daylight, always. So the second one, she gives you the first 2. This is the fall equinox. So it occurs on September 21st. If she didn't put this, it could be either equinox. You can't really tell the difference because they both look exactly the same. It's just where the sun is directly over the equator. And that would be a solar declination for that day. And daylight patterns everywhere on Earth on an equinox will get an even 12 hours of day and 12 hours of night. So this one, the sun is directly over this line of latitude. It's kind of hard because the circle of illumination is over the shaded area. But it's over this line of latitude, which is the Tropic of Capricorn, or at 23.5 degrees south, and the Arctic Circle is completely in darkness, whereas the Antarctic Circle is completely in sunlight. So this would be December. Oh, that's not how I want to do this. that looks dumb, but December 21st. So this would be our winter solstice, and they do call it the opposite in the Southern Hemisphere. This would be their summer solstice, but it's our winter solstice because it's the middle, technically the middle of our winter, but it's the first start of our winter day or winter season. The sun is directly over 23.5 degrees. There's going to be longer day lengths in the Southern Hemisphere and shorter days in the Northern Hemisphere. Specifically, this day, December 21st, will be the shortest day of our whole year. And then after that, the days will start to get longer and longer, and then until the sun is again above the 23.5 degrees north latitude, and then that'll be our longest day of the year. And then the last one is just the spring equinox, same thing. The only difference, solar declination is the same, it's the equator. Day length patterns, 12 hours day, 12 hours of night in both, anywhere on Earth, and the spring equinox, which is on March 21st. And I think this was something I can't click on. You can click on this. I think it has a link in the, it has a link in the PDF where you can go to it and like watch the sunlight changing over the Earth. So these are the terms you'll need to remember. Oh, anyway, this is the terms you need to remember for this lecture. Remember what insolation is, the relationships, and then the 4 important days specifically, those 4 important days in the Earth-Sun relationship. And those will come up a lot. So I did that one in about 25 minutes. Does anyone need a break, or do you want to jump into the third one and get it done? And you're allowed, of course, like to turn off your thing and go to the restroom or go get something to drink. And I don't really care if you eat. If you're sick right now, you need to do whatever you need to do to like stay healthy. So, all right, we'll go into this last one. So this one is just global energy balance. So a lot of this is going to relate to this last lecture we just went over. So this is going to talk about what happens to the insolation or the sun's radiation when it enters the atmosphere. And then what happens to the energy that makes it through the atmosphere and actually reaches the Earth's surface. And then we're going to talk a little bit about greenhouse gases. The participation challenge for this one, or participation points, and this is just going to be helpful for like the class, because this class is weather, climate, and climate change. It's just to think about as you're going through, and I'll talk about a couple of these points at the end, about how the things we're talking about and the global energy balance, how humans can alter parts of this energy balance. So there'll be a couple of times, like at least twice. I wrote down like 3 things when I was going through this lecture last night. So this lecture is going to have certain points that you could go, oh, that's how like a human could screw this up, not screw this up, but alter it, screw it up too. And then we'll go over that at the end. All right, so talked about gases that are in the atmosphere, the principal components of the atmosphere. So gases, it's mostly, our atmosphere is mostly made up of nitrogen, oxygen, but there are a whole lot of other trace gases and stuff, greenhouse gases. There are also solid particles. Solid particles can mean like aerosols, it could mean dust, pollen, things that like get just blown up into the atmosphere. Later we'll call it condensation nuclei, but you don't need to know that term until we talk about like thunderstorms and rain and stuff. And then like drops of liquid or water vapor, which can also be counted as like a trace gas too, but water vapor or cloud droplets. All of these components are going to interact with incoming solar radiation and outgoing radiation that's being re-emitted by the Earth. So how does the sun interact with energy, or how does our atmosphere interact with energy from the sun? And these 4 balls or globes are going to be used as kind of like examples. So there are 4 ways that we talk about that the atmosphere interacts with insolation. The first is transmission, which means that with this globe, if energy were to hit it, it's just going to go straight through it. So that's what it means by transmitting energy. It's just transparent to it. It just goes straight through. It doesn't really do anything to stop the energy. Another one is scattering. So this is kind of like a bumpy globe. So energy could hit it, bounce off of it, and go in all directions. So that would be called scattering. The two biggest ones we'll talk about are absorption. And this is a black globe. So it's very dark. It's going to absorb a lot of energy. So absorption. And then a reflective surface is going to reflect energy. Albedo is a term that we will talk about a lot in this class, and that will come up. Actually, I can't remember what lab it is, like lab 4 or 5 will be like the basis of your entire lab. So albedo is something important that you need to remember from this lecture and make sure you understand well. And albedo is just the percent of energy that is reflected off of a surface. Reflected, not absorbed. So which of these properties apply to atmospheric components? All of them do, just depending on the component. Am I going too fast? Are you okay? Cool. All right, so insulation pathways and how insulation is intercepted by the atmosphere. So gases in the atmosphere are going to absorb or transmit certain wavelengths, depending on the wavelength. Usually they're going to absorb shorter wavelengths and allow longer wavelengths to come through. And this is why things like gamma rays and X-rays don't really make it through our atmosphere. And I said earlier that there are different types of ultraviolet wavelengths or radiation. There are 3 that we talk about: UVA, UVB, and UVC. UVC has the shortest wavelength and is the most dangerous to living organisms. So that is the type that could that's the type that would just burn you to a crisp. It wouldn't just give you a sunburn, it would just kill you. That's going to be absorbed pretty quickly in the stratosphere, the very little that makes it to the stratosphere. UVB is a little more dangerous. That's usually the more cancer-causing ultraviolet radiation. Very, very little of it, like 5% of it, of UV radiation that makes it through at all is UVB. Most of the ultraviolet radiation we get is going to be UVA radiation. And that's at a longer wavelength than these two. So that's why it's able to get through and not be absorbed by like ozone in the stratosphere. So shortest wavelengths are going to be intercepted at higher up in the atmosphere. So gamma rays, X-rays, etc., are not really going to make it very far. They're going to be absorbed really quickly or intercepted very quickly. The ultraviolet radiation that does make it through to the stratosphere is going to be absorbed by ozone. To go over ozone more in just a second. Whereas visible light can get through all the way through to the Earth. It's much longer, at a longer wavelength, and then you have your shortwave infrared that can make it through also. So ozone. I don't know how much you guys know about ozone. It's interesting to talk about. So ozone is going to mostly be concentrated in the stratosphere, the bottom of the stratosphere, which is why the bottom of the stratosphere is the warmest part of the stratosphere, and then it gets cooler as it gets like further high or higher up in the atmosphere. So most of the ozone is going to be right over where the troposphere transitions into the stratosphere. And ozone is comprised of 3 oxygen atoms. The oxygen that we breathe is O2. So 2 oxygen atoms. You cannot breathe ozone. Ozone would destroy your lungs. It's also, when ozone is in the troposphere, it's a harmful pollutant. It's a component of smog. So it's not good when it's in the troposphere, but in the stratosphere, it saves us from being burned to a crisp or all getting skin cancer and dying. So ozone is incredibly important. And I'm sure you've heard of it because you've heard about like the ozone hole, which is not so much of a hole anymore. It's probably one of the most successful policy stories in like our contemporary like political history, that we actually like got together with a whole bunch of other countries and actually like kind of bandaged the hole that showed up in like the 80s and 90s. Let's see. So this is how ozone acts or behaves in the stratosphere. So this says UVC. UVC is going to hit most, it's going to be the one that's absorbed the most by ozone because it has a shorter wavelength. It strikes oxygen gas, O2, or it can strike ozone, O3. When UVC or radiation is absorbed by ozone or oxygen molecules, it causes the oxygen bonds between those atoms to break up. So if you have an ozone molecule and it absorbs or it interacts with ultraviolet radiation, it's going to cause the bond between two of the oxygen atoms and one oxygen atom to break. So it'll break off into one little oxygen atom and then an O2. And then if it is absorbed by O2, it would cause those two oxygen atoms to break apart. So you have all these little like abandoned oxygen atoms all over like the stratosphere. And the thing about oxygen atoms is that they're super needy. They need to be bonded to something else. They don't like, I don't mean to, I personify things when I try to explain them. They don't like being alone. They need to be bonded to like other atoms or molecules. So they're constantly trying to like rebond and recreate or replenish the ozone that is in the stratosphere. So that's what happens when radiation interacts. It breaks these bonds apart, and then they replenish themselves because they're constantly trying to rebond with each other. And so if they run into each other, they'll immediately bond. But the bonds aren't very strong. They're pretty weak, which is why the radiation is able to break them apart when it's absorbed. So why the stratosphere? It's a good combination of where you have oxygen and ozone. And this is where UVC kind of, it's like a sweet spot where they hit in the atmosphere or come together in the atmosphere. There wouldn't be enough oxygen or ozone if you were higher up because there are less molecules in the atmosphere higher up. But basically what you need to know is that ozone in the stratosphere absorbs harmful UV radiation. And that's why the ozone layer is so important. Everyone good with that? So the ozone hole was something that occurred that we noticed in the 80s and 90s. And in the 90s, I think, I used to know all of this, but a bunch of countries got together and were like, we have to fix this. We did this through CFCs, which are chlorofluorocarbons. CFCs are created by human activities. A lot of them were like refrigerators or AC units. They've all been updated now, but there's still some like antique ones that are out there. My house is like 100 years old and it has an AC unit that if it leaked, it would leak CFCs. And we found that out only like 2 years ago. And I was teaching a climate change class at the time and was like, this is the most like ironic thing. But CFCs are what destroy, basically what they do is they keep ozone from replenishing itself. So they'll find a little lone oxygen molecule and that chlorine from like the chlorofluorocarbon and will join with it. So it can't join with like an O2 molecule or O2 or other oxygen atoms that are floating around. So ozone isn't able to replenish itself in the stratosphere, and that's what caused the hole in the ozone layer. So it was improved by policy. That looks terrible right there. It looks like a giant hole compared to this one, but it has actually like improved in the 2000s since we input policies to control or ban CFCs. And the hole also occurs over the Antarctica. That's because there is a very strong current going around Antarctica that once these like CFCs through wind patterns, global wind patterns, like make their way down to the Arctic or Antarctic, they get stuck there and they just kind of sit there. And that's why the ozone hole occurs over like Antarctica. And this is just an example of what like a chlorine atom will do to keep oxygen or ozone from replenishing themselves in the stratosphere. So so that's enough about like the ozone layer. So how much insulation actually reaches the Earth? So of the 100% of energy that actually enters the atmosphere, 49% is actually makes it to the Earth's surface. 20% is absorbed by particles or molecules in the atmosphere, and 31% is reflected by the atmosphere or scattered by the atmosphere. So those three numbers, 49%, 31%, and 20% are important to remember. And then this is talking about what happens to that 49% that does make it to the Earth's surface. So just because it makes it to the Earth's surface doesn't mean that it's absorbed. It depends on what kind of surface or what type of surface that energy encounters once it actually like gets to the Earth's surface. So this is where albedo comes in that we talked about earlier, that percent of reflected energy. So having a high albedo means that most of the energy that encounters a surface is going to be reflected. This is going to be like white surfaces. White surfaces are incredibly reflective and will reflect up to like 95% of the energy that makes it to it. It'll just reflect back off, bounce off, and go back into the atmosphere. Big parts of this would be big examples of this would be like ice caps, ice sheets. Any parts of those are going to reflect most of the energy that encounter that surface. As it gets darker, it's going to, that surface is going to absorb more energy. So let's see, forests are going to reflect about 10 or only 20% of the energy and then absorb the rest of it. So that's a lot that it absorbs. Grasses are going to do about the same. Crops, a sandy desert would reflect about 30% and absorb about 70%. Water depends on how warm the water is or where it's at. That's a whole other like discussion. So yeah, but the way that we try to measure albedo and the way you'll do it in your lab in a few weeks will be based on basically like the color of the surface that the energy is encountering. So lighter surfaces reflect a whole lot more. Darker surfaces are going to reflect a whole lot less and absorb a lot more. Yeah, I didn't really know the purpose of this slide other than to show like where the energy is seen here. I'm sure the energy is wherever the sun is hitting the Earth's atmosphere, Earth's surface. So that would be where the energy is. Okay, so the global energy budget. So everything we just talked about is all in this one map. These orange boxes are what we talked about, those three numbers you need to remember. The percent reflected off of the particles in the atmosphere is 31%, or scattered or reflected. Energy absorbed by the atmosphere, particles in the atmosphere is 20%, and then energy that reaches the ground is about 49%. But again, once it reaches the ground, it doesn't mean it was absorbed. It could be reflected back off, but a lot of it's going to be absorbed. All right, so everyone good with that? I think we only have a couple more slides. I'm trying to remember what this one was about. So this one was kind of asking like clouds in the Earth's radiant energy system. Oh, that's just Sears. Okay, yeah, that's a satellite. So this is asking what type of energy is shown here. This is shortwave radiation energy. So shortwave, again, is going to be shortwave radiation from the sun that's making it through, like trying to make it through the atmosphere and be absorbed by the Earth. So why is it so high up in the northern hemisphere and so low, so dark blue down in the southern hemisphere? I'm actually going to make one of you answer this. I don't know if Mallory and Jack are there, but like if anyone wants to answer that question, why is there so much like shortwave radiation up in the northern hemisphere and not in the southern hemisphere? This is the hint. Just gonna go, I'm gonna go by the looks on your faces that you kind of get it. So it's May. So the sun is going to be over probably really close to where the Tropic of Cancer is. So the solar declination is going to be over the northern hemisphere as opposed to the southern hemisphere, which is why there's so much shortwave radiation occurring here. And this is reflected. Oh, sorry. So that's part of the reason why there's so much shortwave being reflected. I'm sorry, I forgot to point that part out, and so much not being reflected down here. Why is it being really reflected? And one of you actually, I'm gonna like call on Ethan or Alexis, sorry. Why is there so much being reflected at the North Pole if the solar declination is like right here? What's up at the North Pole that could like reflect radiation?
Snow.
Yeah, snow, ice, thank you. So there's a lot of snow and ice up here. Again, there's a lot of snow and ice over Antarctica too, but the sun's declination is over the northern hemisphere right now. So we're not seeing a lot of like reflected shortwave radiation down here as we are up in the northern hemisphere. And that's just from the date. But yeah, most shortwave radiation that reaches the surface in the North Pole and then sometimes at the South Pole, depending on what time of the year it is going to be reflected off. I spent more time on that than I meant to. So what happens when the energy actually reaches the surface, which we've talked about, it's either reflected or absorbed. But what happens when it's absorbed? It can be converted into other forms of energy. It can warm our Earth and our atmosphere. Latent heat can be stored in water and then released later, like with evaporation and to fuel storms like hurricanes. And again, this is from like 2 lectures ago. The first lecture we went over, the Earth absorbs shortwave radiation and then re-radiates long-wave radiation. So the Earth's estimated energy balance, if too much leaves, so this is kind of like common sense, but if too much energy leaves, the Earth will cool because it won't absorb enough energy. If too much stays, it'll be warm. So there needs to be a balance between incoming shortwave radiation and outgoing long-wave radiation. And this is where greenhouse gases come in. So you have shortwave radiation that comes in and actually makes it through the atmosphere and then makes it to a surface that absorbs most of it, and then it's re-radiated as long-wave radiation. That long-wave radiation can warm the Earth, but it's still headed out to space. So what's going to keep it close to the Earth's surface to keep the Earth's surface warm? And that's what greenhouse gases do. So what do greenhouse gases like carbon dioxide absorb? What do they transmit and what are the consequences of this? Greenhouse gases absorb long wave radiation and then transmit means what goes through them. Short wave radiation can go through them. So if you have incoming short wave radiation, it's just going to be transmitted through those greenhouse gases. That's why they call it a greenhouse. So you have a greenhouse like near a garden or with a garden inside of it that allows energy to come inside of it because it's shortwave energy that's coming from the outside. And then it's absorbed by that surface inside the greenhouse and then re-emitted as long wave energy. And then is just bounced back and forth between the greenhouse roof and the surface inside that greenhouse. And that's how the Earth's surface works. So long wave is going to be absorbed by the Earth, re-radiated, and then absorbed by greenhouse gases, re-radiated back to the surface, absorbed by the surface, re-radiated back out, and they just bounce back and forth between the two, and that's what keeps the Earth's surface warm. If we didn't have, what are the consequences of this? Well, we would have a warm Earth. If we didn't have greenhouse gases, we would be an icicle. We would not have a livable surface to live on if it weren't for greenhouse gases. They are incredibly important and we have to have them. Yeah, I looked at this last night. I didn't totally understand it. There would not be green anywhere on here, an Earth without an atmosphere, without the greenhouse effect. Yeah, I'm just gonna skip that one. So, oh yeah, going back to, sorry to switch, but really fast before we end, going back to the participation challenge. Right, so the several ways that humans could alter different parts of the energy balance. I don't know, like, I know you guys are probably really busy trying to just listen to what I said. But But if you were to do this activity, one of the ways would definitely be, probably the most obvious one we talked about would be the ozone layer. So we affect ozone by the release of CFCs and other things. I think they're called HFCs that are becoming a problem or have been a problem now into the atmosphere. So they're released into the atmosphere and can cause holes in the ozone layer. So that's a huge one. Another one would be if we heated if we're warming our atmosphere right now. And as we warm it, it causes more ice to melt. So if more ice melts, then there's less ice to reflect energy. So more energy is going to then be absorbed by the earth coming from the sun. So more shortwave radiation will be absorbed, which is going to then further warm the earth, what you would call like a positive feedback mechanism. The same issue with like larger deserts. So if desertification is occurring, and this one's kind of like further out there, but if desertification is occurring because the Earth's warming, that also means that there's going to be more absorption, because you saw that sandy surfaces absorb like 70% of the, 70% of the radiation that they encounter. They only reflect 30%. We'll have more grasses and forests as opposed to snow. So that kind of goes in with that one. That's a way that we could affect our energy balance as well. So the two big ones are, we kind of have screwed up the ozone layer in the past, that we could do that again or continue doing it by like relaxed policies that actually fixed that hole. And also that we could affect the surface of the earth and the reflectivity of the earth and how much energy is actually absorbed by it. Are there any questions about this lecture? Sorry you came in. I told you to come in, Natalia, whenever, and then I just like got right to the end. But this is recorded, so I'll put it on YouTube for everyone to look at. Does anyone have any questions about any of the lectures? Just, yeah, so that was a lot. We just went through 3 days of lecture in like an hour and 20 minutes. Okay, well, I'll go ahead and stop sharing. If anyone has any questions that they think of later, just email me. Is there anything anyone else wants to know? I know Natalia and Jack, if that you guys will be getting, along with everyone else here, will be getting online lab 2s and possibly lab 3s. We have both of them set up in case you miss next week too, because I don't know how long you have to quarantine. So those will be done online. If you're one of my students, which I think Ethan's the only one, just get it to me when you get to it. You'll need to talk to your TA and make sure that they're going to be really easy on you guys. They want to make sure you keep up with classwork, but also, and don't miss anything, but also you're trying to keep up with a bunch of classes at home right now. So they'll be cognizant of that. And I will talk to Myra and find out what's going to happen if you miss your exam next week, or how she plans on doing that. We want to make sure that you're ready for the exam next week. I'm pretty sure it's next week, September 2nd. So that'd be like next Friday, right? For sure, yeah. So if you're still quarantining, we'll figure out what to do about that. You're not going to fail it. No one's going to fail anything while you're quarantining. That would be cruel and ridiculous. So, and we'll do another session like this next week. If you guys are we still have people quarantining, we might have more quarantining. I mentioned earlier that we're in kind of an outbreak, but they're hoping it'll kind of fizzle out by October. So we are expecting that more students might be in the same situation. So we will let you guys know when we'll be doing this again. I'll probably be at the same time next week, maybe a little later. I had to do it a little bit later or earlier because I have a meeting at 1, but I won't have next week. So yeah, if you're still quarantining next week, we'll probably do this again with lectures for next week. We will be sending you, if you haven't gotten it already, lab 2 and possibly lab 3 to do online. And if you have any questions, you can email me, email Myra, or email your TA if I'm not your TA. All right, does anyone have any questions?
Where is this going to be posted again?
Oh, YouTube, and I'm gonna try to do it on YouTube, but I will send you all a link, all of you, before or as soon as I get it up, which will probably be in like the next 10 or 15 minutes.
All right, thank you.
Yeah, no problem. Any other questions?
I joined at like 11. I was wondering how much like I missed at that time.
I think I had just finished, I think, yeah, when you joined, I just started, I did 3 lectures and I just started the 3rd one.
Okay.
But again, I'm posting this whole thing on YouTube. So you'll be able to go over the first 2. And I did them each in about 20 minutes. So
Okay.
not like horrific to go through.
Okay, thank you.
Mhm. I think if that's it, I'll let you guys go. Good luck. I hope you all feel better.
Thank you so much for doing this.
No problem. Bye, guys.